Okay, this is the lecture video for lesson 6-1, which is titled Justifying Statements. This is the second video out of 3 for activity 3/6, and the quiz on activity 3/6 deals with 3-1, 6-1, and 6-2. So we're starting activity 6, 2 lessons in there, and the activity 6 is titled Proofs About Line Segments and Angles. So we'll be starting these geometric proofs. You've already done these algebraic proofs in lesson 3-1. We'll be moving on to geometric proofs now. But before we do that, we're going to talk about what you have to do in the ways of justifying statements. That's part of your proofs that you'll be doing. If you remember from lesson 3-1, you have the list of reasons. Okay, this is what we'll be talking about. We'll be talking about taking a statement and then giving it a reason in this lesson. Okay, but for geometry. Alright, so let's look at our learning targets. Scratch out the second one, we're not even doing that. For this one, we will be using definitions, properties, postulates, and theorems to justify statements. Okay, so last lesson we introduced two-column proofs but with algebraic equations. Since this is geometry, we will now shift to proving geometric statements, specifically statements about segments and angles. So that's what we'll be doing. We'll be starting with just segments about segments and angles. Later on in other chapters, we'll deal with more geometric stuff as we learn more. So for geometric proofs, there are 3 basic requirements for constructing a good proof. Number 1, we need awareness and knowledge of the definitions of the terms related to what you're trying to prove. So anything you're trying to prove is going to deal with some type of geometric situation, I guess. So you need to be aware and be knowledgeable of the definitions that deal with that particular subject, I guess. Yes. All right, number 2 is knowledge and understanding of the postulates and previously proven theorems that relate to what you are trying to prove. So we want to know the definitions, and we also want to know any related postulates or theorems that have been previously proven to what we are trying to prove. And I say previously proven because we cannot use theorems to justify a statement if it hasn't been proven before, because we wouldn't know it was true. So, all right, number 3, we want also knowledge of the basic rules of logic, just so things flow in a logical order. Okay, so if we need to touch more on this later with terms of logic and how things flow, we most certainly can, but right now we're just going to rely on what we know about the basic rules of logic. Okay, all right, and then, so to write a proof, you must be able to justify statements. So that is the name of the lesson today. So obviously we will be justifying statements. All right, so you should have that proof terms list that I gave you and that you have been adding to, or you will add to later. This will be used. We're going to use that list today to pick these reasons that we will use to justify statements. Okay, so P1, fill in the blank to name the property, postulate, or definition that justifies each statement using the figure to the right. So we have this figure right here on the right. Our first statement in A is if angle ABE is a right angle, then the measure of angle ABE is equal to 90 degrees. So it's a definition of. So I'm going to take a guess that it's going to be definition of right angle, because we're dealing with a right angle. So I'm going to go to my list. We look at definition of right angle, which happens to be up right here. Okay, it says an angle with a measure equal to 90 degrees. So the statement says if the angle was a right angle, then the measure is equal to 90 degrees. That's what our definition of right angle tells us. So this will be definition of right angle. Okay, next. If angle 2 is congruent to angle 1, and angle 1 is congruent to angle 5, then we can say that angle 2 is congruent to angle 5. Alright, so if we remember from last lesson, we talked about the transitive property. This is the transitive property, and let me explain why. Okay, I have 2 things, namely angle 2 and angle 5. they're both congruent to angle 1. Alright, obviously if two things are congruent to the same thing, then they have to be congruent to each other by the transitive property, which would give us then that angle 2 is congruent to angle 5. Another way to think about it that may work out and lets you see how the transitive property works a little bit better is you can write it like this: angle 2 congruent to angle 1, which is also congruent to angle 5, so 2 and 5 have to be congruent in that just long line of equal signs like that. Okay, so another way to see it, 1 just happens to fall in the middle, and like I said, this is the transitive property. I know people get confused, and it's easy to confuse the transitive property and the substitution property. Transitive property, I always say, is kind of like a fancy substitution. It's a specific instance of using substitution. Okay, so what we call the transitive property because it's different than the substitution property altogether, but it's its own little substitution. All right, C. If B is the midpoint of segment AC, then segment AB is congruent to segment BC. Okay, this is a definition. I'm thinking if we're talking about a midpoint right here, this is going to be the definition of midpoint. And in fact, if you look on your list, the definition of midpoint says midpoint is a point on a segment that divides it into two congruent segments, which we have right here, two congruent segments. Okay, awesome. The measure of angle 2 plus the measure of angle ABE is equal to the measure of angle DBE. We're on D right now. So if we look at our graph, we have the measure of angle 2. We have angle 2. We have angle ABE. Okay, so that's that right there. All right. So it says the measure of 2 plus the measure of ABE is equal to the measure of DBE, which is the whole angle, right? So I know that there's a postulate that tells me if I add the measures of the two smaller angles, I get the measure of the outside angle. And so we're talking about adding two things together. So this is the angle addition postulate. So we're using this one kind of only when we're talking about measure plus a measure equals a measure, not when we're dealing with any type of numbers in there. So this type of statement would be by the angle addition postulate because of that. So you wouldn't see like measure of angle 2 plus measure of angle ABE is equal to 180 degrees per se, because that's not what the angle addition postulate tells us. We don't deal with the numbers for that, I guess. Okay, awesome. Moving on. E. If angle 1 is supplementary to angle FBG, then the measure of angle 1 plus the measure of angle FBG is equal to 180 degrees. We know that if two angles are supplementary, then they add up to 180 by the definition of supplementary angles. I'll write it out for you. Okay, so we're going to use the same drawing for our P2, but in this case now we will be we're going to be naming this. We're going to be doing the same thing, naming the property postulate or definition that justifies each statement, but we're not going to be filling in the blank this time. We're going to have to figure it out on our own. Okay, so it says EB plus BG equals EG. So EB plus BG equals EG. Right? Cool. So I'm adding the lengths of two segments to equal the length of the segment they create together. So we're adding two segments. This is going to be the segment addition postulate. Okay, see the similarities between this and what we did with angle addition postulate. There has to be three just different segments referred to in their length. No numbers whatsoever to use this. Okay, awesome. Next, if angle 5 is congruent to angle 6, then ray BF bisects angle EBC. Okay, our key word in this one is this, bisects. All right, so the answer is the definition of angle bisector. Alright, so let me explain why. The definition of angle bisector says that it is a ray that divides an angle into two congruent angles. Okay, so bisect is in there. Okay, we know bisect means to divide into two things that are equal or congruent. Okay, we have a ray that's doing the bisecting. We know that an angle bisector is a ray, and then we're bisecting an angle. We're dividing an angle into two congruent parts, which are angle 5 and angle 6. So let's check and make sure the drawing works out for that. Angle EBC. Okay, cool. And then BF, awesome. And then 5 and 6 are congruent because of that BF splitting that in half. That's what the definition of angle bisector says. So, or in general terms, it says that a ray that bisects an angle to form two congruent angles. Yeah, that's what we are saying, but just with the specifics using this drawing. Okay, definition of angle bisector. Awesome. C. If the measure of angle 1 plus the measure of angle 5 is equal to the measure of angle 6 plus the measure of angle 5, then the measure of angle 1 is equal to the measure of angle 6. So let's write it down again right here. Measure of angle 1 plus measure of angle 5 equals the measure of angle 6 plus the measure of angle 5. Alright, so I want to get measure of angle 1 equals the measure of angle 6, right? So I notice that both the left and right hand sides of the equation have the measure of angle 5. So if I just subtract the measure of angle 5, I'm going to write this in different colors. Excuse me. Then I'm just left with the measure of angle 1 equals the measure of angle 6, which is what the second statement says. So all I did here was subtract the same thing from both sides. So the answer for this one is the subtraction property of equality. So this is the example shows us that we don't just have to have x or y to be able to do this, okay? It means literally any number we can add or subtract from both sides and still use this property, okay? Alright, D. If the measure of angle 1 equals plus the measure of angle 6 is equal to 90 degrees, then angle 1 is complementary to angle 6. Alright, so we know that if two angles add up to 90 degrees, that they are complementary, right? And then we also know if two angles are complementary, then their measures add up to 90 degrees. What tells us this is the definition of complementary angles. So this D is justified by the definition of complementary angles. Like I said, which just tells us that if two angles add up to 90, then they are complementary. Or kind of the other way around as well. So, okay. Awesome. Number E, I think this is. If the angle STR is a straight angle, then the measure of angle STR is equal to 180 degrees. Very similar to the definition of right angle that we did earlier in our first example. This one is very similar, but instead it's a straight angle. So this one is the definition of straight angle. Awesome. Next. Now, we've got a new drawing. It says P3 says using the figure to the left, write a statement that is justified by the given justification. So now we're writing a statement. We have a little more freedom with this. We can write with what's any statement from here. Okay, there's a bunch of different ones we can do, but let's look at part A. The reason that we're given is definition of supplementary angles. So that means that the two angles are going to add up to 180 degrees. Alright, so let's see. how about angle DBA and angle 5? So the measure of angle DBA plus the measure of angle 5 is equal to 180 degrees. We see they form that right in. So that is an example of something you might see. You know, we also might use what we call the linear pair postulate, and we'll introduce that in the next thing. So you would normally see if, so this is probably more accurate, if angle DBA and angle 5 are supplementary, then the measure of DBA plus the measure of 5 is equal to 180 degrees. Okay? Alright. Number B, where we want to give a statement that is justified by the definition of angle bisector. So, let's look here. What do any of these angles kind of look congruent to you? How about 5 and 4? So, we could say that if angle 5 is congruent to angle 4, then ray BH bisects angle, and that's angle is going to be ABG. So ray BH, this ray right here, is going to bisect this angle ABG to create 5 and 4 being congruent. So angle ABG. Okay, remember keyword bisects. The statement had to have that in there. All right. Also, another statement you could have written with the same information would have been if ray BH bisects angle ABG, then angle 5 is congruent to angle 4. For any definition you have, the statement can be written both ways, frontwards and backwards like that, I guess you can call it. Okay, you can switch up the if and thens. Alright, C, segment addition postulate. That means we're adding the lengths of two smaller segments that make up a bigger segment. So how about segment DB, the length of segment, so DB, then you could do plus BH equals DH. How about that? DB plus BH equals DH. Okay, cool. There's not the only segment we could have done, but that one worked, so that's one we're going to deal with. Angle addition postulate. Now I can say that if two angles add up to give me another angle, we talk about their measures. So I could say that angle 2 plus angle 3, measure of angle 2 plus the measure of angle 3. Let's add those two. Okay, they're next to each other. The measure of angle 2 plus the measure of angle 3 equals, alright, so those two together make up this angle right here, and we'll call that the measure of angle EBG. So that equals the measure of angle EBG. Awesome. It's not the only statement we could have done, but that's one of them, and that's what we're going to do for this one. Alright, 4. P4. Write and justify two statements based on the information in the figure. So I have this right angle GFJ. How about that? One statement could be where you're given, so if angle GFJ is a right angle, then the measure of angle GFJ is equal to 90 degrees. Okay, cool. How about another one would be the measure of angle GFH plus the measure of angle HFJ is equal to the measure of angle GFJ. That works too. Segment addition postulate, this angle, GFH plus H of J equals GFJ. Okay, next, P5. Given segment RS and segment ST share endpoint S. Based on this information, Michaelis says that the segment addition postulate justifies that the statement RS plus ST equals RT. Is there a flaw in Michaelis' reasoning, or is she correct? So, first glance, we're going to say, we would think yes, okay? She's definitely she is, there's no, I guess, excuse me, there's no flaw in her reasoning. Because, sure, this makes sense, right? But, we have to think, so Michaela is assuming that the setup looks like this. R, S, T. Okay? But all we really know is that RS and ST share endpoint S. It means they're attached at, those two segments are attached at S, right? That's all we know. We don't know that S, R, S, and T are all collinear, meaning they're all on the same kind of line. We don't know that S is on segment RT at all, actually. So all we know is this. So think about this drawing. What if I have RS right here? Okay, RS. And then we know they're attached by ST. So what if this is ST? Okay. So in this case, let's look at what Michaela's statement says. RS plus ST is equal to RT. Okay. RS right here plus ST. The length of RS plus the length of ST is equal to the length of RT. Okay, so in this case, of course, that's not correct, right? This length plus this length is going to be greater than the length from R to T. Okay, so we could not use this statement because we're not. The segment addition postulate only works whenever your two segments look like this and they're all on the same line. Usually you'll see if S is between R and T. Okay, that's how that works. So because all we know is that RS and ST share endpoint S, we can end up with a drawing like that, and then we could not use the segment addition postulate. So there is a flaw in her reasoning because of the ambiguity and the lack of information from the given statement. Okay. And lastly, P6. Given the diagram, which I do not have right here, I will draw it out for you. A, B, C. And this is D. Okay, so we know that this should also be measure of angle DBC is equal to X. Okay. So measure angle ABC is 90 degrees, so we got that box right there. Measure of ABD is 2x plus 5, and this one is just x. So it's to solve for x, write out every step you take when solving. So I know that the measure of angle ABD plus the measure of angle DBC is equal to the measure of angle ABC. This angle plus this angle equals the whole angle. Okay. Next would be I have expressions for all these. These are my given statements right here. Okay. So let's plug in what we know. We know ABD is 2x plus 5. We know DBC is x. And we know it's equal to ABC, which is 90. Okay. Now we solve a little bit. We get 3x plus 5 is equal to 90. We'll subtract 5 from both sides. We get 3x is equal to 85. And then excuse me, what did I do? Oh, on the notes I made it. Oh, excuse me, guys. Excuse me. On your notes, this should be 2x plus 6. I believe that's what it is. Okay, so this will then be 84. Okay, and then x will be equal to 28. Okay, so let's talk about what we did and justify each step in there. The first one would be just the angle addition postulate. Okay, and then we just substituted what we knew in. Substitution. Okay, and then we simplified our equation. And then we subtracted from both sides. The same thing. So this is subtraction property of equality. And then we divided both sides by the same thing. This division property of equality. Yeah, that's it. So guys, what we basically did right here is we solved and found solved a geometric problem, and we justified each step using what we knew, and that's a geometric proof essentially. Okay, we essentially just did one without actually doing one, and yeah, so that's what you can expect in lesson 6-2. This has been lesson 6-1 on justifying statements. If you have any questions at all, please email me, hunter.patton@cpsb.org. Alright, thanks for watching and have a great day.